Okay, so I'm going to share to you the topic of ionization energy. So definitions of first ionization energy is actually energy required to remove 1 mole of electron from 1 mole of gaseous atom to give 1 mole of gaseous ion with the charge is +1. So basically, if we can write the equations for the first ionization energy is actually, for example, here we have a mg. So it must be in the form of gas or gaseous state, okay, to give mg plus g plus e minus. So amount of electron is 1. Okay, so 1 electron is dismissed from magnesium atom in the form of gaseous state. So that's actually the first ionization energy. How about the second ionization energy? The second ionization energy is energy required. Notice here it says that required. Required means that we need energy from outside. So meaning the nature of ionization energy is actually endo. All right, so it is actually endothermic reaction. So it is energy required to remove 1 mole of electron from 1 mole of gases +1 ion to give charge +2. So basically you have a, if I continue to remove electron from Mg plus, right, then it becomes Mg2 plus G plus E minus. So it becomes always releases 1 electron, and then the charge increases. And then you also need to remember that the state symbol should be in the gaseous state. Okay, so again, let me reiterate, is actually endothermic reaction. All right. Okay, so how about this one? Okay, so excuse me. So how about this um, factors that influence the ionization energy? Okay, so the factors that affects ionization energy is actually size of the positive nuclear charge. Okay, so if the size increases, its attractions for the outermost electron increases, more energy is required to remove electron, and therefore ionization energy increases. Okay, so nuclear charge is actually number of proton. Okay, so basically it's number of proton. As you know, from left to right, number of proton increases. All right, from left to right, the number of proton increases. So it means that in general, let me emphasize again, in general, the value of ionization energy increases because the more proton or higher or more positive nuclear charge. And then the second factor is actually the size of atom. In this case, it's actually distance of the outermost electron from nucleus. If the size of ion increases, the attractions of positive nucleus decreases, and then less energy required to remove electron. Okay, so for example, if we compare helium, all right, or helium to with, for example, lithium 3. Okay, so lithium is only has 2, right? So there are 2 electrons in the outer shell. Okay, 1 and 2. Okay, and then so here you have a 3. Okay, 2 and 1. Okay, so you have a sorry, this one is actually I'll just write here. So it is actually 1. Okay, so so 1 cell, so no more cell here. Okay, only 1 shell. Okay, so so here these 2 electrons is closer to nucleus, so it will increase the effective nuclear charge. If you imagine that you have a nucleus, okay, so actually nuclei, right, and then you have a outer shell electron. So let's say this is electron, and in neutral atom there will be like bonding between this electron and the nucleus. We call this one effective nuclear charge. So this one actually effective nuclear charge. So if the effective nuclear charge increases, means that it needs more energy to break this bonding, right? To break these attractions. So then it will give you higher ionization energy. Okay. All right. So The third factor is actually the shielding effect. So it means that the shielding effect is also related to our the value of the Einstein energy. Okay, so because we see that the shielding effect is from left to right. Okay, as the shielding effect increases, the attractions of the positive nucleus for the negative electrons decreases, and less energy required to remove electron, and then Einstein energy decreases. Okay, so shielding effect can be imagined like you have a um, trend from top to bottom. For example, from lithium to, if you compare to lithium and sodium. So lithium, you only have 2 cells. Sodium, you have 3 cells. So meaning the more cell you have, the less attractions between the electron and the uh, nucleus. All right. So this one is stronger because the distance between because the shell, the shielding effect is literally like the how much energy needed to to maintain this electron. This one is further than compared to lithium. Then this for attraction between electron and the nucleus in sodium is weaker than in lithium. All right. Okay. So next is we can actually find the exception, like a few exception that may arrive in this one. Is actually let me erase this one. First, actually, aluminium, right? So aluminium, if you compare the first Einstein energy, aluminium and magnesium, aluminium is lower than magnesium because here you have a 3p1. Okay, so we have a 3p electrons in Al and 3s electron in Mg. Okay, so we have one electron in the outer cell, which is further away from the nucleus. So it also experiences slightly better shielding. So this one electron is less attracted to nucleus, making it easier to remove this electron. Okay, so how about this? If we compare boron and beryllium, beryllium has a 1s2 to s2 configuration. Boron has a 1s2 to s2 2p1. Again, you have 2p electron. This one electron in 2p orbital is less attracted to nucleus, meaning the energy needed to remove this electron is smaller than the energy needed to remove these 2 electrons, which is tightly bonded to nucleus. Okay, so if you compare S and P, the other exception is actually S is actually 16, P is actually 15. So it is actually 1s2, 2s2, 2p6, 3s2, 3p3. Here the same 1s2, 2s2, 2p6, 3s2, and then 3p4. If I just draw the outer cell, so I will have a 1, 2, 3, 4, and then I have a 3 electrons. So 1, 2, 3. So we have a this upward and downward arrow is basically electron. When 2 electrons close together, they will repel each other. So when we have this kind of circumstance, then this electron can be separated because basically they repel each other. Okay, therefore the first Einstein energy of sulfur is lower than phosphorus because we have an issue of spin pair repulsion. Okay, so when we have spin pair repulsions means that the electron is repel each other, so it is less tightly bonded to nucleus, then it requires less energy to separate them. So it will have a low Einstein energy. Okay, so let's practice this one, our understanding. Why the atomic radius of element in third period decreases from sodium to chlorine. So from sodium to chloride or chlorine, so what we can see is actually in the periodic table, it increases nuclear charge. Okay, so when the increased nuclear charge or the number of proton increases, means that electron, okay, electron. So basically, before I explain that one, so let me just show you this one. Okay, so basically, if we compare sodium and let's say Al, all right, so Mg, sorry, for example, Mg. So Na, right, so we have a 281, so you have one electron in the outer cell. Okay, Mg, you have 282, means that you have two electrons in the outer cell of Mg. So meaning, what we can compare and contrast, Mg has one extra electron than sodium, meaning we keep on adding electron in the same cell or in the third cell of this atom. Okay, so it makes that um, electrons, okay, electrons are in the same cell, are in the same shell, okay, or they are in the same shielding, right? So, all right, so therefore it will increase the effective nuclear charge. So meaning the size of Mg is smaller than size of Na, because the new added electron will be attracted greatly to the nucleus, so making that Mg is slightly smaller than Na. Okay, so this is actually Mg, this is actually Na. Okay, and then lastly, the radius of the most common ion is Mg smaller than radius of the most common ion of S. Okay, identify both ions. Okay, so basically we can approach these questions by saying that we have a magnesium. Okay, we have a magnesium 2 plus, and then we also have a S2 minus. So okay, so Mg, just look at the periodic table. When you have a atom located in group 2, so there will be a Mg2 plus. And since sulfur is located in group 6, then it will have -2 charge. So size of Mg is smaller than size of for example, I'll just draw the outer cell, right? Okay, so size of Mg is smaller than size of S, because in S you have the new added electron. So let me just write this one in red. So we have an additional electron in S. So for example, the original electron of S is in green. Okay, so S in group 6, so there will be 6 valence electron, 1, 2, 3, 4, 5, and let's say this is basically 6. Okay, all right, so now this red sphere is basically the new added electron. So what happens when we add electron in the same cell? It will create repulsion. So when this repulsion occurs, it will decreases it will weaken the bonding between the electron and the central atom of S. Okay, so meaning the size of S is pulling out toward this outside, like this one. So meaning the size of S is increasing because of the repulsion between the new added electron with the existing electron, and it will weaken the bonding between it will weaken the effective nuclear charge between the nucleus with the um, outermost electron. Okay, so I hope you gain something from me today. Thank you so much for watching.